Welcome back to our series on statistical mechanics. In the last episode, we saw the evaluation of partition function for a classical harmonic oscillator in the 2D dimensions. Today, in this episode, we will be dealing with the harmonic oscillator, but that based on a quantum mechanical assessment or a quantum mechanical treatment. Quantum mechanical harmonic oscillator. Here we will be calculating what? The partition function for the system. Last time we were dealing with the 2D situation, the classical situation, and therefore to start with, today we will be dealing with the 2D situation, right? So after that, I will try to cover in a very brief manner also about the three-dimensional system. So the 2D harmonic oscillator, since it is quantum mechanical, what is the first step we need to do? Like in the last episode, here also we need to write the partition function expression. Last time we were writing the single particle partition function. So let's start with the single particle partition function in this situation also, as Q1 is equal to, here since we are here dealing with the quantum mechanical situation, instead of the integral we need to do the summation. Q1 is equal to summation over n Gn e raised to minus beta En. Please note that this small n over here is not the number of particles. Instead, it represents the tag or the number of the energy levels, because we know that, right? We have various energy levels like this, E0, E1, E2, E3 and so on and so forth. So this 0, 1, 2, 3 are in fact our small n. Now, so this is the expression for our single particle partition function. So naturally, now what all things we need to calculate? We need to calculate the Gn and the En, right? So if we get the expression for the Gn, which is the degeneracy, and En, which is the energy corresponding to the nth energy level, we will be able to substitute that over here and calculate the partition function, the single particle partition function, and from there we will be able to extend or extrapolate the single particle to the n particle partition function. So since this is a quantum mechanical situation, first and foremost, how to proceed? We need to write the Schrodinger equation for the situation. So what is the Schrodinger equation for a harmonic oscillator? H cut squared by 2m into dou squared by dou x squared plus we need to write the potential energy part, which is half m omega squared x squared, right? Wave function psi e is equal to is equal to Ex psi, right? So this is the way we write the harmonic the Schrodinger equation for the situation, right? Now in the since we are dealing with the harmonic oscillator, like I told in the last episode, here we are necessarily concerned about a symmetric harmonic oscillator, which is oscillating in a symmetric manner. And therefore, corresponding to the y-axis, I can similarly write in right below the factor for the let me write it down over here. H cut squared by 2m dou squared by dou y squared plus half m omega squared y squared psi e is equal to Ey psi xy. So this is the Schrodinger equation corresponding in the y direction of the situation, and correspondingly, what is the value of E value? Since we are dealing, this is a very basic situation in the in the analysis of a harmonic oscillator, which is the energy can be expressed in terms of the quantized levels, and therefore I can write Ex is equal to n plus half h cut omega, right? This is a very general expression. E is equal to nx plus half h cut omega Ex, and correspondingly we have the Ey is equal to ny plus half h cut omega, and that can be generalized as En is equal to n plus half h cut omega. Sorry, we have the Ey over here, and then we can combine En is equal to Ex plus Ey, right? The energy in the x direction plus the energy in the y direction. And if I consider that nx plus ny, nx and ny are two numbers, right? Are two integers. So nx plus ny can be another integer which I represented by n, and therefore if I substitute those ideas into that earlier expression for Ex and Ey, I can write En is equal to n plus 1 h cut omega, right? So this is the energy for our classical quantum mechanical harmonic oscillator. Now we got the En. Now what else? Our next task was to find out the multiplicity of the system, which is Gn, right? Now here in the case of quantum mechanical case, to evaluation of the Gn is a bit tricky. Now we can have different kind of expressions for that purpose, and many times we need something called the unity operations in order to carry out that kind of analysis. You know the unity groups, right? SUT, unity groups. This kind of unity group analysis will be needed to calculate and to determine in an exact manner the multiplicity of the 2D harmonic oscillator. We are not going into the such kind of calculations, but here generally for a 2D harmonic oscillator I can write Gn is equal to n plus 1, because this is the solution for the SUT oscillations. There is an easy way of understanding this. Let me try to get that point across to you. See, we have this kind of an energy level over here. And here I can have, say, different energy levels, which is 0, 1, 2, 3, etc. Right? Here, my question is that if I ask you, write down the multiplicity in each of the energy level. Here, this is 0, n is equal to 0, n is equal to 1, n is equal to 2, etc. Right? N is equal to 0, which means what? Which means that I have only one possibility. What is n? N is equal to nx plus ny, right? N is equal to nx plus ny. If my n is equal to 0, which means that nx and ny need to be 0. That cannot be negative numbers, right? Because both are some numbers which are only positive integers because they are counts. So nx and ny are the only possibility. That means my degeneracy in this level is 1. N is equal to 1. What is the possibility? I can have two different possibilities, right? 1, 0. That means nx is equal to 1, ny is equal to 0. And alternate situation, nx is equal to 0, ny is equal to 1. Which means that 1, 0 and 0, 1 are both possible situations. And therefore, I can write the multiplicity corresponding n is equal to 1 as 2, right? Take the level n is equal to 2, right? How many levels are possible? There also I can write, there are various possibilities, the 2, 0, 0, 2 and 1, 1. These three possibilities are possible for n is equal to 2, which means that my n is equal to 2, the degeneracy would be 3. If I extend this one, I can go on writing like this, and this can be generalized by the expression degeneracy is equal to n plus 1 in the case of a 2D harmonic oscillator. 2D means what? I have only two things, nx and ny. But if it was a 3D, I will have nx, ny and nsh, which we are not doing it here at this point of time. So Gn is equal to n plus 1. So that is why I took the Gn equal to n plus 1, and in the previous slide we had calculated the expression for the energy also, right? No. Right, En is equal to n plus half h cut omega, and both those expressions we will substitute in the expression which we find out for the single particle harmonic oscillator. And at this point of time, I should give you certain expressions which are available for the 3D harmonic oscillator, for the Gn, so that you can do the expression and do the calculation for that purpose. Gn is equal to n plus 1 into n plus 2 divided by 2. So this is the expression for 2 factorial, sorry. Yeah, and the 2 factorial and 2 are same, but in any case it is 2 factorial, it should be written more appropriately as 2 factorial. Gn is equal to n plus 1 into n plus 2 by 2 factorial. This is the same situation if corresponding to a 3D, right? If it was a 4D oscillator, my Gn can be written as n plus 1 into n plus 2 into n plus 3 divided by 3 factorial. N plus 1 into n plus 2 into n plus 3 divided by 3 factorial, right? So these two expressions you can keep it for your future evaluations for the higher dimensions of harmonic oscillator in the case of quantum mechanical treatment. So for our purpose, let's continue with the substitution of En and Gn in the case of the single particle partition function, which we did, and then I can write that as equal to Q1 is equal to sum over n is equal to 0 to infinity. What was that? Gn, right? So we have calculated as equal to n plus 1 into e raised to minus beta n plus 1 h cut omega. So this was the expression which we found out after substitution, right? Now I need to simplify this expression mathematically. How to do that? let's do one thing. We will substitute n is equal to 0, n is equal to 1, 2, 3, etc. into this expression and make it a series, right? So n is equal to 0, which means that n is equal to 0 means my first factor would be minus e raised to minus beta h cut omega. That will be my first term. What will be my second term? N is equal to 1, which means that it is 2 e raised to minus beta 2 h cut omega plus, similarly I will have 3 e raised to minus beta 3 h cut omega plus etc. I will go on like that, right? Now in this series, my life would be easier if we take e raised to minus beta h cut omega outside. Then in that case, I can write this as equal to e raised to minus beta h cut omega square bracket 1 plus 2 e raised to minus beta h cut omega plus 3 e raised to minus beta 2 h cut omega plus etc. Right? Right. So what is this? This means that this gives me a some kind of a series actually, right? 1 minus x raised to minus 2 can be expanded as 1 plus 2x plus 3x squared plus etc. 1 minus x raised to minus 2 equal to 1 plus 2x plus 3x squared plus etc. So which means that this series can, or the function which is within the square bracket can be written in terms of 1 minus x raised to minus 2, where x is equal to e raised to minus beta h cut omega. And then in such a situation, I can simply write the expression of q1 as equal to, I have the e raised to minus beta h cut omega in the outside the square bracket, and therefore I can write e raised to minus beta h cut omega divided by 1 minus x raised to minus 2. Therefore, I can take it to the denominator. I can write it as 1 minus e raised to minus h cut omega the whole squared. So this is the expression for the single particle partition function in the case of a 2D quantum mechanical harmonic oscillator, and correspondingly I can write the n particle partition function as equal to qn is equal to raised to n, e raised to minus beta h cut n omega divided by 1 minus e raised to minus beta h cut omega raised to 2n, right? So this is the expression for the n particle partition function for a for a quantum mechanical 2D harmonic oscillator. Now we can go on like this. Take this partition function and calculate the rest of the thermodynamical parameters like internal energy, Helmholtz free energy, and the entropy, etc. And that is one way of going on with that. And I would suggest that you should try to solve all those things in your homework, and try to see that you are getting it most simplified. Now, one thing which I would like I would like to cover in this episode would be to deal with a 3D harmonic oscillator, right? Which I think I promised you in the few minutes before. There in the case of 3D harmonic oscillator, the expression was n plus 1 into n plus 2 divided by 2 factorial, right? What was the expression? for that one. That was the case for the 3D harmonic oscillator partition function, right? There also we need to start with the single particle partition function, right? And we know the expression Q1 is equal to sum over n is equal to 0 to infinity the e raised to minus beta en into GE or G simply, right? Or G, right? Here also we will need to have the value of En and the Gn. So in the case of a 3D harmonic oscillator, what would be your En? Now you will know better because we have already done the case of 2D harmonic oscillator, and there we have Ex is equal to Nx plus half h cut omega Ey is equal to Ny plus half h cut omega, Ez is equal to Nz plus half h cut omega, etc. And E is equal to En. En is equal to Ex plus Ey plus Ez. And if I add all of them together, I can write N is equal to Nx plus Ny plus Nz. Like I told last time, Nx, Ny, Nz all are some kind of integers, and therefore I can consider another integer n as Nx, Ny plus Nz. And I have half plus half plus half, which is 3 by 2, right? So therefore I can write the expression for En as equal to n plus 3 by 2 h cut omega, n plus 3 by 2 h cut omega. Right? Now what is my next task? My next task should be to calculate the value of Gn, which I have already written as equal to n plus 1 into n plus 2 divided by 2 factorial. So what should I do now? I should substitute the value of En and the Gn into this expression and simplify this one, right? Which on substitution I can write it as equal to Q1 equal to integral summation n is equal to 0 to infinity n plus 1 into n plus 2 divided by 2 factorial e raised to minus beta n plus 3 by 2 h cut omega, right? So this is my expression for single particle partition function. Like we did last time, now I need to give the values for n as 0, 1, 2, 3, etc. And then I can write this as a series as the following: e raised to minus e raised to minus 3 by 2 h cut omega, of course beta, e raised to minus 3 by 2 beta h cut omega plus we have n is equal to 1 there, which is 2 plus into 3, which is 6 there, and then divided by 2 factorial, which I can write it as 3 e raised to minus beta 1 over there, 1 plus 3 by 2, which is 5 by 2 minus beta 5 by 2 h cut omega, and so on and so forth. You can calculate it with substituting n is equal to 1, 2, 3, etc. right? And then I can, similarly last time we were doing 1 minus x raised to minus 2. Here I can substitute the expression for 1 minus x raised to minus 3. 1 minus x raised to minus 3. What is 1 minus x raised to minus 3? It is 1 plus 3x plus 6x squared plus etc., which I can substitute which I can substitute with this expression. I can, and then therefore I can simplify that expression for q1 is equal to e raised to minus 3 by 2 h cut omega divided by 1 minus e raised to minus beta h cut omega raised to 3, right? E raised to the minus 3 by 2 h cut omega beta h cut omega divided by 1 minus beta h cut omega raised to 3, and correspondingly we have the qn is equal to e raised to minus 3 by 2 n h cut omega divided by 1 minus e raised to minus beta h cut omega raised to 3n. So this is the partition function for a 3D harmonic oscillator in a quantum mechanical treatment. So like I told you last time, again if you know the expression for qn, I can definitely calculate the factors for the A, CV, etc., and then continue with the derivation. So that is it. So to recap, we had taken the partition function, we evaluated the expression for the partition function in the case of a canonical ensemble. There in the canonical ensemble, we were dealing with the situations where the energy, only the energy is allowed to vary, right? Most of the, as I told you that time, most of the physical situations are actually in turn connected with the variations in the energy. So we calculated the partition function for the system as equal to, we calculated the partition function in terms of the energy. Qn is equal to e raised to minus beta h cut omega. There, next what we did was that we introduced the concept of degeneracy into the expression, and therefore we put the degeneracy in two ways. One is for the classical situation and another is for a quantum mechanical situations. For the classical situations, we were taking the case as a purely continuum where we use the integral, and for the quantum mechanical situations, we were using a discrete situations, which is the summation situation, and therefore we have two expressions there. And then we took the case of a classical ideal gas, which is there we assume that the energy is allowed to vary in that between the particles. And then that's a very typical situation for a canonical ensemble. And so then we did that analysis, and then we calculated the partition function for a classical harmonic oscillator. Classical three-dimensional ideal gas. Then another typical situation where which is very much applicable for the canonical ensemble situation would be the harmonic oscillator, where we have analyzed three situations. One is the classical two-dimensional harmonic oscillator, where there we have calculated the partition function. And if you remember the partition function expression, we calculated in terms of some kind of some factor which you can relook into that into that episode or your notebook and see for yourself. Then what we did was that we calculated the same situation of the harmonic oscillator in a quantum mechanical approach. But now what I want to tell is that now if we look into those expressions for the classical and for the quantum mechanical in the two-dimensional situation for a harmonic oscillator, the question which I want to ask is that where do you get the same expression for the partition function? Now the answer is that no, the partition function value which you get in both the situations are different. Now how will you account for such a situation? Because we have physically we have only one situation, which is a harmonic oscillator. We are doing it in two different treatments. One is classical and another is quantum mechanical. How is it possible that if you do the classical we get one expression, and if you do the quantum mechanical we get another expression? How is that possible? Actually, we will reach the same expression provided we do the assumptions which categorizes between a quantum mechanical and a classical situations, which I am not dealing it here. We need to make the assumptions, and then you will see that the partition function for the harmonic oscillator in the classical and the quantum mechanical can be approximated to the same expressions within certain limitations, which I leave it to you, which you can ask me in the interaction sessions if you are planning to attend, so which I leave it to you. And then we took a fourth situation, which is a 3D harmonic oscillator, and there we calculated the expression also, which is similar to the 2D harmonic oscillator in the quantum mechanical, and then we calculated. And there are various other problems. One of the very relevant problem which you could look for yourself is the paramagnetic electron situations, which is very relevant in the case of magnetic evaluation of any system. Again, there also when you apply a magnetic field, actually you are allowing the energy level to change, which means what? Which means that I need to approximate it to a canonical ensemble situation, right? Because when we are applying a magnetic field, we are not changing the number of particles, right? If we were changing the number of particles, we could say that no, it does not belong to the canonical ensemble. So one can calculate the paramagnetic situation in using either quantum mechanical, right? Quantum mechanical or classical situation, and for the magnetic case based on the canonical ensemble. So we will end this episode with that note. In the next episode, we will be dealing with the situation where we allow the number of particles also to change, which we call as the grand canonical ensemble, which we will do in the next episode. Thank you.